Hi everyone, this is Thiagarajan, retired Deputy Chief Engineer from Indian Railways. So in this video, I am going to explain about the design of various parameters of the curve in Indian Railways, namely the superelevation and the maximum permitted speed on the curve, how it should be calculated, and also how the cant deficiency in the cant excess are being utilized effectively for fetching the maximum parametric speed, and also length of transitions. So all those things we are going to discuss with worked out example. In the previous video, I have discussed about the design aspects of the curve. That is the limiting values of the various parameters, and also the various formulae are being used, okay, for calculation of the various parameters and designing the curves. So this idea will go into the subject. So before going into the occurred example, let me recollect something about the limiting values of the various parameters. Okay. Of course, radius, it is as discussed, it is based on our site conditions, importance of the route. Okay. And coming to the maximum cant, it is limited to 185 mm in case of group A and B route, and 165 mm in other routes. Okay. This limiting value has been set, based on the safety point of view and as well as the comfort point of view. See, sometime there are chances for stopping the train on curve. Okay, so when the train is at rest, what will happen? There won't be centrifugal force acting on the body, acting on the vehicle, and in the absence of the centrifugal force, the entire load of the vehicle distribution will be towards the inner rail only. And also with this, you see, when there is a wind force heavily, it is in unfavorable side. That means when it is blowing towards inside, towards inside of the curve, the joint together, that condition will become worse, and there are chance for the overturning with respect to inner rail may happen when the limit is exceeded, when the cant we are providing more than the limit. Okay. And also, you see, the passenger comfortness also you have to see. When the train is stopped on a curve, the people and the passengers who are sitting on the train also will feel some discomfortness. They are, slightly they may leaning towards inside. They have to adjust themselves. Okay. So these also one of the reasons for which we are in compulsion to restrict the maximum cant on the curve. Okay. And also in case of goods train, sometime there will be a empty wagons will be there. When empty wagon is there, when the train is at rest, what will happen? The outer will get floating, will be in floating. Okay, because load distribution will be inside because of the emptiness. The outer wheel, that the absence of sufficient load, that wheel will be in floating condition, and will try to start. What will happen? It may, try to maybe climbing over the outer rail. It may result to derailment. So that is why this has been limited to 185 in the case of group A and B routes and 165 in other routes. Okay. And coming to the cant efficiency, 100 mm, 150 mm, it is for nominated rolling stocks. Okay, this will be certified by the RDSO. So certain rolling stocks, have been certified 100 mm cant efficiency and 150 mm cant efficiency. That is given for certain rolling stocks. And other rolling stocks 75 mm. This is also the limited. The maximum is limited to 150 mm. It is based on your again safety and the comfort point of view. So when the train is running at a speed on high speed, what will happen? There will be cant efficiency. That normally will be expected by the high speed trains, passenger trains. Okay. what will happen in this case, when the unbalanced force, because the current deficit, certainly there will be unbalanced force will be there. When it is running in equilibrium speed, okay, the current will be exactly, because of the current, the forces, centrifugal force will be exactly balanced. There won't be any unbalanced force. When the train are moving with some current efficiency, there will be some unbalanced lateral forces. You should be within the limit. Okay. As per the some literature, you see, you can 0.1 g, that is 1 meter per second square. If you exceed the limit, passenger will feel some discomfortness. So, and also safety point of view, see, already there is unbalanced force acting away from center. At the same time, there is a wind force that is also acting, away from the center. What will happen? Join together, this situation will become further worsened. There are chances for the overturning against the outer rail. Okay. So that is why it has been limited to maximum 150 mm. Okay. Be something about the current efficiency. This you have to keep in mind how much you have to go for this current efficiency. And coming to the current access, that has been limited to 70 mm for all trains. Here, this also again, as far as current access is concerned, there will be experienced by the goods train. Goods train. So normally goods train will be hauling with a heavy tonnage load. So when normally because of the current access, always load distribution will be inner rail only. When the limit is exceeded, what will happen that more load distribution will be inner rail. Then thereby there will be more wear and tear to the inner rail, flattening of rail top as well as the wear will be more on the inner rail. So that is to be controlled. Also, again the wind force also to be taken into consideration. If there is blowing towards center, already the load is towards inner rail because of the added force. So there are chances for the overturning with respect to when against to inner rail. So that is why there is a need for restricting the current access. So based on these such all situation, safety and these maintenance point of view, that has been limited to 70 mm for all trains. Okay, coming to the rate of change of current, actual current efficiency and current gradient, these two parameters are coming into play in case of designing our length of transition. As far as this is concerned, that is rate of current, actual current efficiency, it is with respect to the speed of the train permitted on the curve. Okay. And the second one, the later one, is current gradient, is with respect to the length of transition, distance traveled. Okay. So the first, desirable is 50 mm per second as well as rate of current efficiency concern, and maximum we are permitting up to 60 per second. That means to get a minimum length of transition. Okay. Suppose in case of space constraint, we are going to the upper limit. Like that, in case of current gradient, this desirable is 1 in 720 and the steepest is 1 in 3 you are permitting in order to get the minimum length of transition. Okay. So these things you have to first keep in mind while deciding what length of transition. So because you see, as far as the both the conditions, just to understand. So normally, the inner rail we are keeping horizontal and whatever superelevation, and we are giving only the outer rail, and we are easing out the transition portion we are easing out in the outer rail. So that will be a gradient rail. Okay. So that is mean this has been limited because the certain exceeding certain limit, what will happen? It will result in some heavy jolting, and discomfort of the passenger. At the same time, also safety point of view also you should consider. Okay. See. For example, this is normally is 2 pairs of wheel, let us take. So already the track, there is a design twist because this is kept horizontal. So whatever is we are giving only outer rail, that is only like gradient. Gradually it is just increasing. So when the trains negotiating or transition portion, suppose let us take 2 pairs of wheel, due to the design twist available, there will be heavy jolting because these 2 rail will be the one inclined plane, other 2 wheels will be in a horizontal plane. So because of the difference, the result, the difference is more, there will be heavy jolting suddenly, when the train entering into this portion, heavy jolting will be there. And also same time, we exceed the limit, what will happen? It's unsafe also. because of this twist, the exceeding certain limit, what will happen? The wheel gets offloaded. The diagonal, this will get offloaded. Simply because of the offloading, it may there are chance for the derailment. Okay, it will go out of path. Okay, so that has been limited to 60 mm in case of all rate of change of cant actual cant efficiency, and cheapest cant getting permitting is 1 in 360. Okay, so this idea we will go into the worked out example how these limiting values are being used for designing of curves. You can see. Okay. Coming to the first one example. Here, this case, you can just read out the questions. Here, it is a group here route. Speed is 160 kmph, sectional speed, and booked speed of train is 65 kmph. And cant efficiency permitted is 150 mm. I'm just taking the maximum item because high speed route at the same time, nominator only of we are permitting 150 mm. Okay, some cases. So that I'm just considering here. And goods train, of course, 65 km. It is a lower speed train. Okay, so with this, we have to find out the minimum radius of the curve. Okay. What should be the minimum radius curve we have to provide in the BG group here route. Okay, that we have to find out. Okay, now 160 kmph, so there is sectional speed, 65 goods train speed, and 150 mm cant efficiency. Here, what we have to do first, we are working out the cant, how much cant you have to provide. That means provide actual cant, how much you have to provide. Consider the cant excess. Okay. Suppose equilibrium cant, what's the equilibrium cant means? That cant actual, the whatever cant required for the goods train speed. Okay. Normally cant excess is coming into play only goods train. That is why goods train we are considering, goods train speed we are considering. For the goods train speed, whatever cant is equilibrium speed, availing or cant excess, that means CA minus cant excess will be your equilibrium speed, or otherwise CA actual cant how much provided equal to the equilibrium, the cant plus the cant axis will be our the actual cant. So, okay. So, this relation, okay, we will go to the next one. Here, since it is not given, cant axis, we are taking 70 mm because 70 mm cant axis for all trains. There is no problem. Even it is not given, we can straight away take cant axis equal to 70 mm. Okay, but other cant efficiency will vary. Okay, it depends upon the raw material rolling stock. Sometimes it may be 150 mm, sometimes it is 100 mm, sometimes 75 mm, like that will be there. So if specifically, if it is there, and we can take otherwise we have to assume. Okay, but here as well as cant is concerned, it is for all trains 70 mm. That is why even it is not given, we can straight away take cant is equal to permitting cant is equal to 70 mm. Okay, so cant axis consideration, this is the cant actual equation. And coming to the cant efficiency constraints, high speed trains, S is missing. High speed trains, you see again that is cant actual equal to this equilibrium cant. Okay, what are equilibrium cant? No, this is particular already we have discussed. That is GV squared by 127 R. Okay, for all cant, for equilibrium cant. That formula only we are reduced. That is in case of BG, giving 1750 everything. Adding it. Multiplying with that. And we are getting this one 13.76 Vm squared by R. Okay, already I think we have discussed the previous slides that I want to using here. So this is equilibrium cant. Equilibrium cant, the total cant required minus cant efficiency will be our actual cant because we are availing our cant efficiency. Okay, in this will be the actual cant we can provide. Okay, permitting this much of cant efficiency, and we can calculate this cant actual in the case of high speed trains. So equating both. So first case, we have one equation we have formed with respect to, cant excess consideration. The second one is based on your cant deficiency consideration. So equating the both, we can find out the R, how much R we can find out. So already we know 13 is a constant. VM already is given. It is 1. This is this case 160 kmph. And goods train is this one 65 kmph. Okay, 65 kmph. Considering this one, see we can find out the unknown. That is from there we can find out the, or equating both the equation, we can find out the R minimum. So finally we are getting the R, how much we can go, the sharpest curvature. Okay, flatter no problem, okay, sharpest only the problem, no. So from that we got the radius equal to 1406 meter. However, we have to check it for cant actual and availing the maximum cant efficiency also, because normally this cant excessive will come into play in case of maximum speed, fastest train. So for the fastest train, so availing the cant efficiency, okay, and the cant actual provided, okay, what will be the radius we have to find out. Okay, here what you are doing further, cant actual plus cant efficiency, because cant actual, whatever they are cant providing plus cant efficiency maximum, okay, that will be your this one equilibrium cant. That means CA equal to this one minus CD. So CA plus CD equal to this equilibrium cant. So from this equation we can find out the how much R it's required. So in this case substituting R, and R we are getting 1051.51 meter. This is it. Our normally we should get the flatter only, because earlier the previous this R minimum we calculated considering both cant excess and cant efficiency consideration. This we got. So now for high speed train, considering the cant efficiency consideration, we have checked up. From this we got R minimum equal to 1051.51 meter. However, we have to choose, we have to provide only the greater one. That means a flatter round radius only we have to provide for safer side. Suppose if you are not providing, if you are providing 1051.51 meter, 1050 meter, what will happen? This will satisfy this speed, cant efficiency, high speed train, but it will not satisfy the cant X consideration. That means when goods trains are running at 60 km, that will experience more cant X's, more than 70 will come. So that is a flat round you have to choose. So finally this will be your the minimum radius we have to provide the curve for this condition. Okay, this is about this problem how we have to work it out. Okay, then we'll go to the next example. The next example, see here they are given the problem BG and curve of radius 870 meter, and the sectional speed is 130 kmph and goods train speed is 3 kmph. Okay, and they are given cant efficiency also, maximum how much permitted is 150 they are given. So they ask here the actual cant how much we can provide. Okay, maximum how much we have to provide, and what is the maximum permissible speed on the curve, and minimum and desirable length of transitions they have asked. Okay, these things they asked. So the first again, as we already discussed in the previous problem also. So first we have to work it out based on the cant efficiency consideration, the cant required for the cant efficiency consideration. Okay, so CA plus CD equal to, this will be your equilibrium cant. So from that we are substituting. So cant efficiency means what we have to keep the speed of the maximum speed. Okay, fastest train speed. So and substituting the here it is 130 kmph. So 130 we are substituting here. So we are getting CA plus CD equal to 265.76. That means considering the cant efficiency this much. But this equilibrium cant actually. But this much we don't provide because we are availing cant efficiency of maximum 150 as given the problem. So in this case actual cant how much you can provide. So total required the equilibrium cant minus the CD permitted maximum 150. That will be your actual cant. Okay, however 120 mm we are providing. Okay, normally whenever we are providing the superelevation, I mean this it should be round off to nearest and higher multiple of 5 normally we are keeping. Okay, so 120 mm we are keeping. Okay, actually this also we will check with the maximum cant permitted is how much for this let us take for cant how much here 180 mm maximum we can permit. It is not there, but actually for group A route so 185 mm we can permit. Okay, with 150 mm rolling maximum now this cant efficiency, so we can permit a maximum cant of 185. So normally group A, B route 185 we can permit nowadays. Okay. So it is within the limit, 125 is within the limit. Okay. Then we'll go to the next step. Next one, we are working on the cant actual required based on the cant excess. So cant excess consideration, what is it? Because cant excess means is based on the good strain speed. So good strain speed is given is 65 kmph. For 65 kmph, what is the cant required? Equilibrium cant required is this much 64. But we can permit some cant excess. Okay. So how much cant excess? 70 mm we can permit some cant excess. That means 66.44 plus 75 will be your actual cant. This much we can provide. Okay, this much we can provide, and even it is required, even for the speed 65.44, 75 mm is a cant excess. This is permitted. This will be the actual cant based on the cant actual. However, so we have to provide minimum values. So out of 2, how much? In the earlier previous case, it was 120 mm cant edge consideration. But here in cant actual cant X consideration is 141. Then minimum of both of 120 and 141, and we have to adopt only 120 mm. So 120 mm adopt, it will satisfy CD conditions, cant edge consideration. But when we are providing 120 here, it will be more comfortable. Okay, it will the cant axis will be actual cant axis will be for when you are providing 120 mm, it is instead of 140, 120, 40 mm less. That means 30 mm only will be around 30 mm only cant axis will be there. So this is safe. Okay. So now actual cant to be provided is 120 mm. So next case, next step, the maximum permissible speed. So already we have decided how much cant we can provide. That is 120 mm. So cant deficiency how much provide also the problem it is given, that is 150 mm. The radius is given 875. So using this relation, the maximum permissible speed on the curve equal to 0.27 root of CA plus CD. This already we have discussed in the previous video. So using the relation, okay, we can find out. Substituting these are the values we are calculating. We are getting 131.23 km per hour. Okay, actually this is actually we can permit this much, but our section speed itself 130. So we can run a normal speed, sectional speed. There is no need of any speed restriction here because the permit this okay, how much we can permit 131, but whereas sectional speed itself 130, that is why there is no speed restriction of 130 kmph. Then we can run the speed at a speed of 130 kmph on the curve. So only the speed restriction. And coming to the desirable length of transition, you see they asked desirable and minimum length, they asked the problem. So already we have seen, we have the 3 conditions, L1, L2, L3. L1 is based on the rate of cant actual, one equation. Second was rate of change of cant deficiency, second equation. Third one is based on the cant gradient. This is 1 in 720 gradient. Okay. This is first one is 50 mm per second rate of cant actual. The second one is 60 mm per, is also 50 mm per second cant deficiency. So this will be the equation, and using this relation we got the first case L1 87.36 meter, and rate of cant deficiency consideration, this is 109.2 meter, and third one with respect to based on your cant gradient of 1 in 720, we calculate as 86.4 meter. So out of 3, greater one you have to choose. So greater one is 109. Normally when we are choosing out of 3, the greater one you have to choose should be multiple of 10 higher side. Okay. Normally in transition length, we are keeping in station units. That means 10 meter interval we are having station. So that is why it should be multiple of 10 meters higher side. Since in the 109 and we are rounding up to 110 meter. Okay. Next multiple of tens. So this will be your desirable length of transition. Okay. And second and next, the minimum length of transition, you see, we have already formula. The same thing, 5/6 of the L1 normally. Okay. That is 60 mm per second cant actual and cant deficiency. And there is 1 in 360 of gradient, cant gradient. So it's half of L3. Okay, the last one is half of L3 because it is 720 gradient, 360 gradient, that is half. So using this relation we can get it. Okay, 5 means what time? That is 50 mm. Okay, this is equation. 60 mm how much? Okay, that's what the minimum length of transitions. So using the relation we got the three values. The first one is 72.8 meter, and the second one 91 meter, and third one is 43.2 meters. So out of three we have to choose the higher one, that is coming, that is 91 meter. And again here to anyway 1 meter extra is gone. Over it for safer side, go for higher side, multiple of 10, that is it will come to 100 meters. So this will be your minimum length of transition, how much. Okay, this is in the case of space constraint. Normally we use this one. However, only 10 meter difference. However, as per this formula, we are only getting this much. This we have to use only in the case of space restriction, and otherwise desirable is only this much. Okay. So this is about this problem. And coming to the next example. So supposing just to go through everything, understand, if you are not clear, not clear, so just pause it off and understand. Okay, whatever I say is understand and proceed to the next example. Okay. So this the third one is here maximum pulse speed of the curve, they given 870 meter. Radius of curve 870 meter, and they asked the maximum speed they asked, and length of transition here restricted to 80 meter. So okay, so maximum speed they asked, but in this case the length is restricted to 80 meter. We can't provide more than 80 meter. So but speed of the section speed of 130 kmph, and current efficiency we can avail up to 100 mm. So this condition we have to calculate the maximum speed. Okay. So that whatever given, no, you just writing down here, and since here restricted length, we have to use the second part, that restricted rate of change of current, maximum we have to avail, that is rate of the current how much normally system maximum we can permit. So that we can consider here, and C post gradient, current gradient 1 in 360 we are permitting. So considering this one, we have to proceed for calculating the maximum permissible of the on the curve. Okay. Here in this case current we are taking 180 5 maximum, because group here route, no, that is 180 we are taking. But current efficiency they are given 100 mm they are taking. Current X of course for all times 70 mm. Okay. Then we proceed. So first case, every time we used to do, first current efficiency consideration we are working out the current required. That's CA plus CD equal to, this is the equation. So consider the current deficient, the actual current we can provide 265.76 mm. Okay. Okay. So here suppose, but actual current in this we can work it out. So considering the current deficiency provided under mm, the actual current we can permit 165 mm. Though it is the equilibrium current required 265. Okay, we not provide this much, we can provide less, no, availing current efficiency. So 265 0.76 minus 100, this will be actual superelevation we can provide. That is 165.76. That is of course we can rounding up to one next lower multiple of normally superelevation lower multiple. Okay, this 165 we rounding off, which is less than 185. Okay, so hence okay here. Okay, it is restricted. Okay, actually not exceeding or maximum current of 185. It's okay. Then coming to the current X consideration, again current X again, we have to use goods train speed, because the earlier case, current efficiency normally we have to use only section speed, full speed we have to max fastest train speed we have to use it. But current X consideration we have to use goods train speed we have to use. So considering the goods train speed, the current X consideration, the current required, equilibrium current required 96.89. Okay. But actual when you are providing 165 mm current, the what will be the current access? The required current is this much. Okay, required this much, but for actual current we are providing how much? 165 mm. So differences will be our current access. that is 68.11 mm it's coming. So this is your cant axis. Actually, when you are providing 160 mm cant, okay, for the equilibrium cant speed, this will be your cant axis, which is less than 75 within the limit. Hence, okay. Okay. So once whatever we have decided, no, whatever we are calculating, that's okay. Okay, you can continue. But with the cant 160 mm cant deviation, another maximum speed, we have to work it out the maximum speed. So already we have considered, we have taken cant actual 160 mm at present, okay, but it may vary because the length of transition has been restricted. But however, for this condition, for this up to this, so we can calculate a 160 mm of cant actual. So with this permitting cant efficiency and using the relation 0.27 root of CA plus CD plus into R, we are working with the maximum speed permitted. That's coming around 130.01, say 130 kmph. Again, we are rounding up to lower multiple of 5, that is 130. So minimum length using this cant actual and cant efficiency, whatever, and the speed, we are calculating the minimum length of transition because restricted this one, no. That's why the second set of equations for calculating the transition, we are using it, and using the relation we got, that is first L1 equal to 100.1 meter, that is cant actual concentration, and cant efficiency concentration 60.66 meter, and coming to the cant gradient concentration, it is 59.4. So out of 3, the greater one is 100.1, over slightly it is exceeding 100, 110 multiple of 10, no, we are keeping it. So this is where actually for this condition, for the cant actual calculated and cant efficiency and all, the minimum length of transition we are provided 110 mm, but we can't provide because here in this problem the L is restricted to 80 meter. So then what to do? You have to for ensuring 80 meter, we have to do some compromise. That means because 110 meter, because of the cant actual, no, since we are providing 160 mm, we got that. So in order to get 80 mm, slightly we have to do some compromise, some reducing our cant actual and cant deficiency, something. Okay, you have to do it something. We'll see in the next slide how it should be done. Okay. Now, see, this is your first one equation, no, for length of transition. 5 is the 0.0056 CA into VM. Here what we are doing, considering the CA for optimization, no, we are considering CA equal to CD. Okay, both limit, no, CA and CD we are limiting and keeping as it same. Okay, CA equal to CD. Then we have first equation, we have the equation of length of transition 5 is the 0.0056 CA into VM. Okay, from this we can calculate VM. So okay, we can reverse it. We are reverse it. Okay, so in terms of VM equal to L divided by 5 by 6 on this one. This is one equation. And second equation we have already, we know pretty well that maximum speed using the 0.27 root of CA plus CD or. Here in this case what you are doing, we are for optimized, for optimization, we are keeping both CA and CD equal, same. That is why here CA plus CD equal to same. That means that here in this case 0.27 root of 2 CA into the second equation. So first equation is VM equal to this one, and second equation is VM equal to this one. So equating both, from there we can find out the CA. Okay, they are not now, because for this condition, now we have to reduce the cant actual in order to get a restricted length of the length of transition. That because it will be restricted to 80 meter. Okay, here since the given length of transition is 80, substituting this, the unknown is only from this CA, we are calculating CA. So from this equation calculation, we got CA equal to 142.43, say 140 mm. Okay, rounding out to the lower multiple of 5. Okay, but we have to check for cant gradient. Okay, this CA and CD consideration, we got this one. Okay, keeping the length of transition, restricted length of transition 80, we calculate the CA equal to 140 mm. So again we check for the can gradient also, that can gradient is more, that is 140 mm, no, 80 meter, so 80 meter. So 140 mm for 80 meter. So how much for 1 meter? That means 80 meter, so 8, that is why 80 meter into converting into mm. 80 into 1000 mm divided by 140, this will be your gradient. Here we got 571.43, okay, but we can permit up to 1 in 360, so it's okay, it is flatter than 1 in 360, so this satisfies the can gradient equation also. And over we have to since already we have consider CA equal to CD, okay. So, but whereas how much we got now, CA actually we got 140 mm. The optimization we have considered CA equal to CD. In this case, CD also 140 will become, but we can't permit 140 mm CD, but it is restricted to 100 mm. Okay. So this is 1 second, just step by step we see, we have to compromise again, going back, it should satisfy everything. Okay, we have to see. And slowly, one by one, each line you just go through, understand, and okay, if you want to not clear, and just to pause it and understand, go to the next slides like that. Okay, so here CA equal to CD, CA is now more than, that is why here again VM equal to 0.27 root of CA plus CD. Here CA we can put down 140, but whereas CD we have to put only 100. We can't go beyond 100 because that is the can efficiency max permitted is 100 mm as far as this problem is concerned. Okay, so with this equation we can calculate the speed, and for this we got 123.73 km per hour, or rounding up to lower multiple of 5, say 120 kmph. So sorry, it is 120 kmph, not this one. This is 120 kmph. This is 120 kmph. This is 120 kmph. This is 120 kmph with the restricted speed, because for 80 meter restricted transit length. So sectional speed is how much? Sectional speed is 130 kmph. So we can't permit 130 kmph. As far as curve is concerned, we can permit only 120 kmph. So to impose SRA 120 kmph on the curve. This is about the this example. Okay, problem. How we have to find out the maximal speed of the on the curve, and the length when the length of transition is restricted to certain length. Okay, now let's see something about the compound curve. Here in this problem, we have to find out the minimal length of transition to be provided. Okay, in between the two compound curves, two curves. Okay. So you know pretty well already we have discussed the formula as far as the compound curve is concerned. That means the between the two curves, and the approach of curve number 1 and the exit point of the curve number 2, that we can solve, find out the length of transition. That is usual procedure. But in the case of the transition, length of transition in between the two curves, okay, for that we have seen the different the set of formula we have seen. Here the first one, as usual, 3 conditions, L1 equal to 0.0056 into CA1 minus CA2. That means cant actual of first curve minus cant actual of second curve into VM. That is based on the rate of change of cant 50 mm. The second one is L2 equal to 0.0056 into cant efficiency of the first curve minus cant efficiency of the second curve into VM. This is rate of cant efficiency consideration, that is 50 mm per second. The third one is 1 in 720 cant gradient based on this 0.72 into CA1 minus CA2. Okay, these are 3 conditions we have. Out of the greater one you have to choose. But here in this case, when we know the cant actual of the both curves, we are able to substitute here directly. We can find out fixing the cant efficiency. Okay, we can find out, but it is not given this formula. They are not given the cant of the both curves. Okay, so in this case we have to find out the for providing the minimum length of transition, how much cant we have to provide for the first curve and second curve. Okay, these are the things given from the problem. As usual, we have to go for the first form the equation for the curve number 1 based on the cant efficiency consideration. Okay, that is equilibrium cant for the that means cant efficiency consideration. That means in this case we have to take a high speed train speed of 100 kmph. So then we get the substituting the value of 100 kmph using this formula. We got the equilibrium cant of 196.6 mm. Okay, cant efficiency constant, that is CA1 plus CD1. Okay, this is first equation we got. Based on that, we got the equilibrium cant of 196.6 mm. Then the second, this is for curve number 2. Okay, based on the for the curve number 2, it's missing here. Curve number 2, we have to find out for the cant efficiency consideration. It's the same speed of 100 kmph, substitute in this 100 mm, and we are finding out the equilibrium cant for the second curve, that is CA2 plus CD2, 137.6 mm. Here for optimum transition, what we have to do, normally earlier case and all, we used to equate both CA and CD. Okay, so that the first two equation, no, when you are optimizing that CA, cant actual and cant efficiency, no, that equation will have the equal length will be there. Okay, so like this here, since we want to calculate the length of transition in between the two curves, then we have to equate the difference of the cant actual of the first curve, second curve, and difference of the cant efficiency of the first curve and second curve. So this is our equation. Okay, to get the optimum transition length. And subsequently, so we are averaging the equilibrium cant of difference of equilibrium cant of first curve and second curve. This is CA1 plus CD1 is equilibrium cant of the first curve. Second curve, CA2 plus CD2 is equilibrium cant of the second curve. Okay, the difference of the equilibrium cant, okay, and averaging the, okay, we get this value that actually that will be your the difference of cant actual of the both curves and difference of cant efficiency of the both curves. Okay, by equating this, okay, we form this equation like this, and from there we are calculating the rest of the values. Suppose for example, for availing the maximum CD of the sharp curve, because normally we have to consider the sharper curve, because here sharper curve is curve number 1. Suppose curve number 2 is sharper curve, that we have to consider the second curve, but here the first curve is sharper curve. So we have to choose a select a sharper curve, here curve number 1. So that CA1, this curve number 1, C actual 1 is equal to that that is 196.6, that is maximum cant, no, maximum cant, I mean first curve number 1, no, cant equilibrium cant of curve number 1 minus 75 mm, that is cant efficiency, equal to 121.6, say 120 mm. So we are calculating 120 mm, that will be your cant actual of the first curve. This 196 is equilibrium cant of the first curve. So availing the cant efficiency of the 75 mm here, and we are fixing the cant actual of 120 mm. Like that, using the equation 1 here, what you see, CA1 minus CA2 is equal to 30 mm. So CA2, okay, then CA2 equal to how much? That this 120 mm, that is CA1 minus this 30 mm. So from that we got the CA2 value of 90 mm. Like that, second equation you take. So substituting the value of the cant efficiency 70 mm. So minus 30 mm will get the 45 mm. So CD2 will be 45 mm. So first curve CA1 is 120 mm, scan efficiency is 70 mm, sharper curve only, that is why maximum CD we want to avail here. And second curve, the CA2 is 90 mm and scan efficiency is 45 mm. Okay, like that we are calculating little slightly, little seems to be a little complicated, and we just understand the concept and we go ahead. Okay. Now coming to the Kant excess consideration now. Okay. So whatever we have done now, earlier Kant deficiency consideration of the both curve IRSE. Now the Kant taking the curve number 1 for 1, the radius is 700 meter. We are finding out the equilibrium Kant for the good strain speed. Okay. So we got how much? 83.05, and already CA1 how much we have provided? 120 mm we have provided for the curve number 1. So how much Kant excess is there? 120 mm, the equilibrium Kant is 83 mm, minus we will get the actual Kant excess experienced will be 36.95, which is less than the 75 permitted, hence okay. Okay. So curve number 1, Kant actual 120 mm is also good here. Okay, because satisfy the Kant consideration also. So coming to the curve number 2, here the radius is 1000 meter radius. We are finding out the equilibrium Kant. Substituting here 65 kmph, we are finding out the equilibrium Kant for the curve number 2, 58.14 for the good strain. This is talking about the good strain equilibrium Kant. So Kant actual. So already we have calculated CA2 equal 90 mm. Then the Kant X actually experienced, for in the second curve will be so 90 mm minus equilibrium Kant required for the good strain, for the second curve 58.14. So we'll be getting net 31.86 mm. That will be the actual Kant excess will be experienced by the train. Okay, in the second curve. So which is less than 70 mm means okay. So here also 90 mm whatever we have decided for curve number 2 was good. So again now we go for the length of transition between the two circular curves. So as already discussed, we have three formulas, and that's we are substituting. Okay, L1 is equal to 0.0056 into CA1 minus CA2 Vm. We got the first condition 16.8 meter, and second 0.0056 into CD1 minus CD2 into Vm. Substituting the value, so we got 16.8, because here since already now we equated, that is almost coming equal. And third one is in sound gradient 0.72 into CA1 minus CA2. From this equation we got 21.6. So this is higher. Okay, now that is why the greater of the three we consider the last one 21.6, and rounding up to the next higher multiple of 10 we are fixing as 30 meter. This will be our length of transition. Okay, that is to be provided in between the two rivers. So I think you have understood this curve, the compound curve, how the length of transition in minimum length we want to do it, we can provide. Okay. Otherwise, as usual, you can calculate the superelevation for the first curve, normal curve, and okay, if there is no restrictions, directly you can use these three equations. You can fix, you can find out the length of transition. Okay. Here we have been asked to find out the minimum length, so we are optimizing and doing it. Okay. So only this thing, the tricky one here. Okay. Okay. Now let's go to the next example. Okay, now we will see the next example. It is the problem from actually Indian Railway Permit Manual, IRPWM, para 4055. So in this example, problem, they are given radius of the curve, but the length of transition is restricted to 40 meters. So I have been asked to calculate the maximum permissible speed and superelevation. Okay. Here, this case, the length of transition is restricted to 40 meters. So, to satisfy this, then we have to work it out our superelevation. And further, what we are doing here, we are taking the two equations, that is speed on transition curve, that formula, and speed on circular curve. I mean, related to transition, no, that formula we take, and as usual, our the maximum permissible of the curve, that formula we have. The two formula we take, and equating that, we are first trying to find out the Kant actual, how much to be provided. Okay. So how it is to be done? See, pretty well your length of transition formula, that is L equal to 5 by 6, actually 5 by 6, not 5, 6 into C into VM. Since why we are using it now? Because now because it is restricted formula, we are taking the 5 by 6. That means 60 mm per second, rate of change of Kant actual. So that we consider here. Consider that equation we take. So if you are converting the formula in terms of Vm equal to, so this will be the equation. Okay. Vm equal to L by 0.083 into 0.0056 into Z. This is one equation. Okay, for finding out the Vm with respect to length of transition, using the length of transition. Okay. So another formula, as usual, we know that 0.27 root of Ca plus Cd into R. But in the manual, the illustration they are given like this. They are used directly. We know the formula, actually this is converter formula, but they are using the direct that formula, that is L equal to 1 by rate of Kant actual into Ca into Vm. Okay. So we are again you are rewriting like this: Vm equal to rate of Kant actual into L by Ca. Okay, from this equation. So here they are equating these two equations. Either you can use this equation or you can use this equation. Both are only the same. Here you have to use some conversion factor and all. Here equating 1 and 2, the RCA into L into 3.6 conversion factor divided by Ca equal to 0.27 into root of Ca plus Cd into R. So this also equation for Vm, this is also equation for Vm, then both we are equating, that is equating 1 and 2, and the only unknown is now Ca. So we are finding the Ca. Here what we are doing for optimization, as usual, we have to take our Cd equal to Ca. That if that is the case, what will happen? It will become 2 Ca, 0.27 into root of 2 Ca into R. Okay. So here, as usual, as already told you, they have taken 60 mm per second for broad gauge. That is the maximum rate of change of Kant actual permitted. They have taken to, okay, for the restricted, since there is restricted length of transition. So equating this equation, substituting all the values, now we are getting solving. We get Kant actual equal to 94.85, say 95 mm. Okay. So next, the limiting value normally we keep 75 mm, that is CD, because they are not specifically there. That means the lower value, that is okay for all other trains. Whatever CD applicable, we take 75 mm, and maximal speed, that 0.27. We can use this here. Earlier, we have, for the purpose of calculating the the Ca, we can 2 Ca we taken, but here we take that CD, or the actual CD we permitted here. So 0.27 is root of Ca plus CD into R, and substituting a 95 and plus 75 into 600, we are getting the maximum permissible speed, that comes to 86.23, say 85 kmph. So the maximum speed is 86.23 and say 85 kmph. So rounding off to lower multiple of 5, okay. We fix 85 kmph, that is our maximum speed. And Kant gradient we are checking here, that is 95, that is a Kant actual divided by 40 meter. So 95 mm for 40 meter. 40 meter we are converting in mm. So 95 by 40,000 will get 1 in 421, which is flatter than 360. Okay, only 1 in 360 up to 1 in 360 we can go. Okay. That's why which is within the permissible limit. Okay. The rate of the Kant actual at 85 kmph works out to 56.07 per minute, and also we are working out the rate of the Kant actual that's coming around 56.07. This we can use the formula 1 by data in the cant actual first formula we are using that formula into CA into BM that formula you can use. Using that we can find out the how much data on the cant actual we are getting it. So we are getting, it works out to that is 56.07 mm per second, okay, which is also within the permissible, because we can go up to 60 mm. Okay, it is less than 60 mm, so it's okay. Okay, everything is satisfies now here. Okay, now let's see a different type of problem. Some sections we will have some mixed traffic. So there we will have a different type of trains with a different tonnage of hauling load, and speed also will be different. So we are just categorizing and by groups, and for we will find out the equilibrium speed. Okay, speed, and after that we will find out the cant equilibrium. So in order to find the equilibrium speed, here we use one formula. It's a Russian formula, and just like it is a weighted average method. Okay, so that formula is the equilibrium speed equal to root of number of trains in the particular group having the tonnage of load and the speed of the particular group. Okay, like that, second category, then third category. Okay, that means that is N1 W1 V1 squared plus N2 W2 V2 squared plus N3 W3 V3 squared, and so on. Suppose now I have taken only 3 groups we have. If we may have some n number of groups will be, so we can just extend further also. Okay, so this divided by N1 W1 plus N2 W2 plus N3 W3 and so on. Okay, root of that equal to that will be your equilibrium. So where N1 N2 N3, okay, so on, number of trains in each speed group, and W1 W2 W3 total weight of each train falling in each group, okay, speed group, and V1 V2 V3 speed of the train in each group. Okay, so the collecting the data, okay, with the available data we can find out the equilibrium speed, and after that we can go for the finding out calculating our cant equilibrium. Okay, we will see the worked out example. Okay, so in this problem, so we've been asked to find out the superelevation and length of transition. Okay, the curve is 500 meter radius, it's located in hilly section. Okay, this is the pattern of traffic. So the first group, it's mail and express and passenger trains, 12 numbers. The total load hauled by these trains is 750 ton, and the speed of the train group is 60 kmph. The second one, goods traffic, that is 7 numbers, 1700 tonnage of load, and 30 kmph is the speed. Okay, sectional speed for the goods traffic. And mixer trains having 2 numbers and 500 metric ton tonnage and 50 kmph, its permissible speed for mixer trains. Okay, this is the data given. With that we'll go into the problem calculating our equilibrium cant and length of transition. So okay, so as discussed, this is our formula V equilibrium. Okay, this is a formula, and as for this case concern, the N1 and N2 N3 W1 W2 W3 V1 V2, so we have got this is given in our problem, and substituting this value here in this equation, we are getting the equilibrium speed that comes around equal to 45.63 km per hour. Okay, the maximum is 60 kmph speed train, express train, and goods train, low speed train is 30 kmph. Okay, and our V equilibrium is coming to 45.63. So for the data given, so here the equilibrium first we are finding out. So pretty well the equation, that is 13.7 for the BG, 13.76 into equilibrium speed square. Okay. Okay, we are finding out the equilibrium Kant. Okay, so 13.76 into 45.63 squared divided by the radius. So that comes around 57.31 mm. Okay, say 55 mm. Okay, then we go for the Kant efficiency consideration. And this is also Kant equilibrium for the high speed train, that is fastest train, no, that is Mail Express. So for the Mail Express, 50 km when it is running, the radius, we want 99.07. Okay, that is required. Super is required is this much. But actually we are providing how much? We are providing only C equilibrium we are providing. So that means 55 mm we are providing. When you are providing 50 mm, the requirement is this much, 99.7. In this case, the Kant efficiency will be how much? 45.07. But it is less than 75, which is within the limit. Hence, okay. Then again we check for the Kant X consideration. That we take for the lowest train speed. That means good train speed. That is 30 kmph. So 30 kmph, we find the equilibrium Kant for the good train speed. 13.76 into 30 square divided by 500 equal to 24.77 mm. Okay, this is our requirement for 30 kmph speed or good train speed. But we are providing how much? We are providing 55 mm. But requirement is this much. The difference is how much? 30.23. It is excess. It is okay. That will be your maximum Kant excess. But whereas our maximum permissible limit is 75 mm. It's within the limit. So hence okay. So since satisfy both the conditions, Kant efficiency consideration, Kant considerations, and whatever we got C equilibrium Kant, that is 55 mm. So that's okay for all the conditions. That is why we provide superelevation of 55 mm. Okay. And next we go for the transition length. Here we take the desirable length of transition. The three equations we find, we take and we substitute the value, and the greatest one we take here. Here, as you already know, this is 0.0056 into CA. CA means what? Actual whatever Kant we are providing, CA into 60. Here we take only the maximum speed. No, we take that is Mail Express train speed, that is 60 kmph. So the first conditions that is 18.48 for rate of Kant actual for that case. And second, Kant efficiency consideration. This is 0.0056 into 45.7. Here it is 45.7 because for fastest train how much total requirement is 99.07, but we are provided 55 mm, that is Kant efficiency actually will be available, experienced by the fast train is 45.07. So that we take here, and into 60 will be your Mail Express train speed. So substituting we are getting 15.14 meter. Then L3, it is a 1 inch 120 gradient, that is 0.72 into CA, 0.72 into 55 mm, that is actual Kant. For this condition, we got 39.6, that is a maximum value, that is why we consider. So this will be our length of transition. Rounding of this one, we provide 40 meter. Okay, this is something about this problem. Okay, the mixed traffic case, so we are using the Russian formula, finding out the equilibrium speed, and for that we find out the equilibrium Kant, and that actually we are providing that. That is our actual Kant. And for the actual Kant, we are checking for Kant efficiency and Kant excess, considering the high speed and good train speed. Then finally we go for the length of transition. Okay, this is the standard formula given. Okay, this is something about this problem. So we'll go to the next problem. Okay, now let's see a different problem, contraflexure, similar flexure. So what is contraflexure, similar flexure? Suppose sometime what will happen, points on crossing will be falling on a curve. Okay, sometime in the points on crossing whatever available in the curve, the turnout side, when it takes off away from the main line, okay, bending opposite to the main line, it's called contraflexor. But the points on crossing turnout is turning inside, that is bending similar to the main trunk, it is called similar flexor. This is the difference. Okay. In the both the situation, how the curve has to be designed, that you have to see first. And before that, you see here, regarding contraflexor, I want to say here one thing. See here, if you take the points on crossing which is on the main track, you see this location. This is your curve, mainline curve. Actually, this is your outer rail, this is your inner rail. Okay. So whereas in the case of turnout side or the branch line side, what will happen? This is outer rail and this is inner rail. That means the outer rail of main track will be inner rail of our this one, turnout side. So when we are providing superelevation to the mainline track, that will become negative superelevation for the turnout side. So because of this critical situation, and we have to design superelevation, provide superelevation such a way to satisfy and both the conditions. Okay, to satisfy the superelevation required for the train which is going on the mainline as well as the train which is negotiated in the turnout also. Okay, duly availed in the permitted cant efficiency. Okay, that aspect you should look into here. And also, as well as of course in the main line, similar flexor, this problem will not occur because the outer rail of the main line and the outer rail of the turnout track will be one and the same. There won't be much problem because same superelevation we are giving to main line. That will be my superelevation for the turnout side also. Okay. But in the case of contraflexor, the situation is different. And also one more thing you should understand. I want to say here. Suppose this is your main line radius, we will be knowing, but we know the radius of the turnout. Suppose we was some 1.8 points are crossing falling on a curve. We know the radius of the turnout. Okay. But when we are providing in the curvature, since the main also bending, following the curvature of the mainline track, so the radius of turnout will not be as it is, it will be flattened because of, you see, when it is bending, automatically this track also pulled this way, this curvature will become little flatter. So for example, this is a mainline straight. This is the radius of straight turnout RS. And or degree of turnout ds. Okay, ds. But when it is straight, so long as straight, it will be as it is. When it is bending, automatically the amount of curvature given to the main, that will affect the radius or degree of the turnout. It will become flatter. For example, here the simple we can say, if you take a degree, the degree resultant will be equal to degree of the straight turnout minus dm. Okay, suppose in this, let us take this 1.8 turnout. This is the 8 degree curvature is there. Suppose 8 degree curvature. When this main line, degree of the main is 3 degree, what will happen? So 8 minus 3 will become 5 degree. It will be flattened because 8 degree curvature, because of 3 degree curvature we are given to main line, automatically it will become flatter, 3 degree will be reduced. So finally the resultant degree of the radius of turnout will be 5 degree. But normally we used to make the equation in terms of radius because for all the purpose we are using radius only for calculation of superelevation, everything. Okay, so that is why in terms of radius this is RR equal to RM into RS divided by RM minus RS. It's nothing but it's simple because dr equal to ds minus dm. Suppose we can substitute here, you know the relation between the degree and radius. So degree equal to what? 1 by 1750 divided by r. Okay. Like that ds 1750 divided by ds and dm 1750 divided by dm. So substituting here, we want to get the RR Okay, rearranging the equation, we'll get this equation. In case of contraflexor, the resultant radius is equal to Rm into Rs and Rm minus Rs. So if the problem they are given some unit of, and using the relation we can find out the radius of resultant of the turnout, and using the radius we can find out the superposition required for the branch line. Then we can check up the how much superelevation we can give to the main line. Okay, this is the way. Normally the same turn we are assuming same curvature, the branch also will continue for further. Okay, this situation. In case of similar flexure, this you have to understand. Here it is different. Here, because since it is fluxing, bending in the same direction, the degree radius will be ds plus dm. So already it is having some 8 degree, let us assume, and further 2 degree main and mean 8 plus 2, it will become further sharpened. Okay, further sharper. That is why this will become 8 plus 2, 10 degree. So in terms of radius, if you want to write RR equal to Rm into Rs, divided by Rm plus Rs. So this is something about the resultant radius. Using this resultant radius, we have to find out the superposition required for the this one, the outside branch line here, or contraflexor side or similar flexor, and after that how much you have to provide to the main line, and we have to decide. Okay, this is something about it. We will go to the workload example. Let us see in detail. We will be able to understand. Okay. And before that, this is something about the points and graph. Just I want to display here to know the radius. Suppose sometime they may have radius of turnout. If it is not given, simply they may say 1 in 8.5 points and crossing on on curve, or 1 in 12, like that. That is the case. You have to use this radius. 1 in of radius is 232.26 meter. And in case of 1 in 12, it is 441.36 meter. It is all in mm. And I'm just saying in a meter. 1 in 16 it is 784.993, and 1 in 20 it is 1283.1. This is the radius of the lead radius turnout of various points and crossing. 1 in 8.5, 1 in 12, 1 in 16, and 20 respectively. Okay, this is something about it. Okay, we will go to the example now. Okay. The first example in this type, you see, 1 in 8.5 points and crossing on a curve. Okay, BG 600 meter radius curve. It is sectional speed is 130 km/h. So we have been asked to find out the permissible speed for the express train and other train, and the speed of the turnout is given as 30 km/h. So with this we have to work it out. How much superelevation we can provide maximum, and based on the superelevation provided, we have to fix the maximum permissible speed of on the curve for the express train, high speed train, as well as other trains. Okay, we will see one by one. First, before that, we have to find out the resultant radius, because see here, this is your main line, radius of main line. What is the radius? 600 meter radius. Here we are providing the the points and crossing is available here. That is 1 in 10 points and crossing. Okay. When the points and crossing straight, you know the radius, that is 232.26. Okay. When it is fluxing opposite direction, that means taking off. So that will not be 232.26. It will be become flatter because of the main line curvature. Okay. So then we have to find the resultant radius of turnout, RR. RR equal to Rm into Rs divided by Rm minus Rs, as we have discussed earlier. So substituting here, Rm is equal to 600 meter and radius of turnout, straight turnout 232.26. We are getting the resultant radius, that is equal to 378.95 meter. Okay. Then after that, see, we have to first provide the cant required for the turnout. Okay. Already given the speed of the train on the turnout is 30 km/h they given. So for 30 km you have to find out the equilibrium cant, that is 7 GV squared by 127 or 13.76 into V squared by R. Any formula you can use it. Using the relation, we are getting the cant, equilibrium cant required for the goods train speed is 32.73 mm. Okay. Here we are using resultant radius. Resultant radius. So this actual cant is required, but we can permit cant efficiency 75 mm. Because since it is a counter reflexor, if you are providing the cant to the turnout side, that will become a negative superelevation for the main line. But we are much concerned about the main line. That is why we should not permit any negative cant. We should not provide to the main. But at the same time, we can permit your cant, negative cant to the turnout side, but duly avail in the cant efficiency. If that is the case, the maximum cant efficiency availed is can be availed is 75 mm. So 75 mm minus the 32.73 mm. This is equilibrium cant. So we can provide a negative cant of 42.27 mm into the turnout side. When we are putting negative cant to the turnout side, that will become positive cant to the main line. Okay. So that is why we are availing full cant 75 mm minus the requirement of cant for the turnout 32.73. It comes to 42.27, and say we are providing 40 mm. When you are providing negative cant of 40 mm to the turnout side, that will become positive cant of to the main line. Here you see, this is your negative cant. This negative cant. That means actually we have to provide a main turnout side like this 32.73, but we are not providing. We are permitting a 70 mm cant efficiency and lowering this outer rail of our turnout side, duly availing the cant efficiency. Once we are lowering, now there will be a cant of 40 mm that will be negative. Once it is a negative, that will become positive superelevation for the main line. Okay. So this way we have to do and compromise in this situation, and we have to provide the superelevation. You have to design the superelevation. Once this is your cant to the main line, with this cant we can work it off over speed of the train. That means for the high speed trains, high speed trains normally we can permit a cant efficiency of 100 mm. So actual cant we are putting 40 mm using the relation Vm equal to 0.27 root of Ca plus Cd into R. So substituting 40 is actual cant and plus cant efficiency maximum for the high speed trains. So radius substituting here, we are getting the speed, maximum permissible speed on the curve for the high speed trains 78.25 kmph. Say 75 kmph. Okay, lower multiple of 5 we are rounding up. So here for other trains, other trains we are permitting cant efficiency maximum of 75 mm only. So here in place of 100 mm we are substituting a 75 mm and we are finding out the Vm that comes to 70.92, say 70 kmph for other trains. Okay. So this is something about the contraflexor. If that is the case, how it should be calculated. Okay. Since it is at this location is very critical, and see, we are permitting negative superelevation to some extent to the turnout side, duly availing the cant efficiency, and from there we are finding out the cant that will be a positive cant. Okay, the whatever negative cant to the turnout will become positive cant, and for the positive cant we are finding out the superelevation, duly availing our cant deficiency. We are fixing the maximum speed of the trains for high speed trains and the other trains. Okay, something. So this you have to once again carefully look into, you have to understand and proceed. Okay, we go to the next example. This next example, it is for the, I think it is for the similar flexor, because a 1/12 turnout takes off from the inside of the curve 8000 meter radius and broad gauge. Maximum suction speed is 100 kmph. Determine the cant and maximum permissible speed. The turnout is not followed by a reverse curve. When turnout is followed by a reverse curve, allowable speed on the turnout is 15 kmph. Okay, here inside 15 kmph speed is turnout side. Suction speed 100 kmph, radius is 800 meter. Here, as already discussed, and see, we have to find out the resultant radius. So that is here RR equal to RM into RM plus R. Using the relation, we have to find out the resultant radius. Okay, so here because of fluxing inside, so the radius will become sharper, because The radius of the 1 in 12 turnout is 441.36. Already I have displayed. This is for 441.36. It is for 1 in 12 radius of the lead curve, turnout curve. Okay, 441. So since because of bending inside the same direction, okay, that since curvature is 800 meter radius is curvature is there. Mainly also has to follow the same radius. Since it's bending in the same side, it will become further sharper. The result radius now it becomes 284.44 meter. Okay. So here, this is your main line track, 800 meter radius. This is a straight turnout 1 in 12. Actually, straight turnout means it is 441 will be there. Since it is fluxing, this is main line is fluxing. Automatically, this also shifted inside. Further, it becomes sharper. So the result radius will become around 200 something. Okay. So as discussed earlier. Okay, this is the way how you are getting the result radius. Okay. Okay, now 284 is the result radius of the turnout side, and we are finding out the equilibrium current for the 15 km. Speed on turnout, the turnout is 15 kmph. So for 15 kmph, we find out the equilibrium current using the relation same 13.7 v squared by r resultant. Let us say r let us take. Okay, so for this speed, we are getting 10.88 mm superelevation required. Say 10 mm we are providing. But current our main line how much we are finding out. So we can permit a current excess. Here we are availing current excess. But 10 mm when we are providing, so we can permit a current excess of 75 mm. Okay. That's why the actual current we can provide plus 75 85 mm. When you are providing 85 mm, what will happen when trains going on turnout 15 kmph? The requirement is 10, but whereas we are providing 85 mm, it will experience 75 mm, okay, which is permissible limit. The excessive current excess will be within permissible limit. So, we actually current how much we are providing? 85 mm we are providing. So, once we are providing 85 mm, so automatically we can find out speed availing the current efficiency. So, when this is actual current, using the relation Vm equal to 0.27 into root of Ca plus D into R, okay. Here our actual current, here 70 mm maximum current efficiency permitted. So with that, we work out our maximum permissible on main line is coming around that 96.59 kmph. So we're rounding up to next lower multiple of 5, let's say 95 kmph. Okay, this is in the case of similar flexure. Okay, in the previous case, we have seen turnout not followed by reverse curve. So this case, we will see turnout followed by reverse curve. Okay. So in this case, this is your main line. This is similar flexure. So immediately after the turnout, there will be a reverse curve. There will be a reverse curve. So because we are providing, superimposed to the main line. Then when there is a reverse curve immediately after the end of the turnout, what will happen? The in between there is a formation of twist, because this superelevation will be we are rising outer rail, and in the case of reverse curve, the outer rail will become inner rail. So there will be formation of twist. That is why you are supposed to ensure in that case at any cost, because of the change of curvature, the twist formation should not be more than 2.88 per meter. This is IRPWM para number 412.2. Okay. In case of any turnout, followed by reverse curve, this is the case. You are supposed to ensure the twist should not be more than 2.88 mm per meter. That is 1 in 360. We are seeing in a transition curve. The same thing. Okay. It should not exceed 2.8 mm per meter. At the same time, we should restrict the superelevation in the main line. So that is limited to 65 mm. Okay. So this thing we have to note down. In case of reverse curve, after the turnout, so we are supposed to follow the IRPWM para 412. There it is clearly mentioned, followed by reverse curve. The change of current on the turnout may be permitted starting begin the crossing after the last exit sleeper and being run out at a rate not steeper than 2.8 mm per meter, and the subject to the maximum count on the mainland turnout being limited to 65 mm. So this thing you should note down. So here that is why earlier we have calculated a superelevation of some 85 mm for the this main line. So this is the case, this superelevation has been restricted to 65 mm, and for 65 mm allowing the cant efficiency and the given radius we have to find out the maximum permissible speed on the curve. So that is the case is coming around 90.36 km per hour, and we are rounding up to 90 kmph. Okay, this is something about it. Okay. Okay, now let's see another different example. These also points and crossing falls on a curve. That is a 1 in 12 turnout takes off from the outside of a 350 meter radius broad gauge curve. Okay, been asked to find out the MPS, that is maximum permissible speed over the main lane. Okay, the speed over the turnout is 30 kmph. It is given. Okay, now to calculate so MPS over the curve, main lane curve. So here you see, so the given is the radius of curve is 350 meter, the main lane curve. The turnout what we are providing is the 1 in 12 turnout. The radius of the 1 in 12 is 441, but whereas the main lane curve is 350 meter. So it is sharper. The main lane curve is sharper than your turnout radius. So whenever the points on crossing turnout tugs off from the main lane curve, that we have to use like a contrafluxure. That formula we have to use. That resultant radius is equal to Rm into Rs divided by Rm minus R. That formula we have to use. Here the radius of the since the radius of the main curve is sharper than the radius of the turnout, so we will be getting the value resultant radius negative. It's coming around 1690.85 meter. It is negative. So since it is negative means what? It is not fluxing in a opposite direction, and it's fluxing in the same direction. Okay. But here the radius of the curve is 350 meter radius means that almost 5 degree. That is 5 degree. But whereas the degree of turnout is 4 degree actually. Okay, 4 degree. So that is why 4 minus 5 1 degree. That almost near closely it is 1 degree will be there resultant radius. That's this direction. Okay, just like a similar fluxure, fluxing in the same direction. Okay. So once we got the resultant radius here, then we have to substitute. No, we have to find out the equilibrium cant using the relation 13.76 into v squared by Re. So substituting here the resultant radius and this speed over the turnout, so we get the 7.02 mm, that is equilibrium cant. Okay, that is required for our turnout. Okay, the train which is negotiating in the branch line, that means through turnout. Okay, the superelevation required is 7.02 mm, that is equilibrium cant. But we can provide still higher, so avail the cant efficiency, because here just like a similar fluxure. So whatever the cant we are providing to the turnout, that will be a superelevation for the main lane curve also. Okay, so here we can avail the cant excess, so we can go up to 70 mm extra, because we can permit a cant excess of 75 mm. So here what we do, adding this one 7.32 plus 70 mm cant is permitted, so actual cant we can provide this much 82.32 mm, say 80 mm. Okay, this will be the actual cant 80 mm. When you are providing train goods train, any this one train negotiating through the turnout of 30 kmph, it requires 7.02 mm superelevation, whereas we provide 82.02 mm, 80 mm. So in this case cant excess will be less than 75 mm, 70 mm less than 75. So that is why we provide availing the cant excess, and we provide actual cant of 80 mm, okay, in the for the mainland curve. That's also the superelevation for the turnout side. So using this, this actual cant, we can calculate the maximum permissible speed on the mainland curve. Okay. As usual, our relation is 0.27 into root of CA plus CD into R. The radius of our mainland curve is 350. So here 80 actual cant provided, plus here cant efficiency also we permit. No. So availing cant efficiency of full cant 75 mm, we work out the maximum permissible speed, that is coming around 62.88 kmph, say 60 kmph. So the mainland speed now has to be restricted to 60 kmph. If it is more than, the section speed is more than this, so we have to impose speed reduction of 60 kmph on the mainland curve. So this is something about this example. Here only different is, here also is taking off, but whereas since 112 the radius is flatter than the radius of the mainland curve. So just like the branch end just fluxing in the same direction, and because of that, the outer rail of the turnout will be outer rail of the mainland curve. So in that case, we are availing the cant axis, and for the superelevation required for the turnout, and we are fixing the actual cant, and then we are working out the maximum permissible speed on the curve, availing the cant efficiency. Okay, the cant actual plus cant efficiency. Using the relation, we are finding out the maximum permissible speed on the mainland curve. Okay, and this is the speed permitted on the curve. Okay, when section speed is more than this, then we have to restrict to 60 kmph. Okay, this is something about this problem. Now we'll see a certain exercise. This question has been asked in UPS Engineering Service 2024. Here, this also you can see here now. This calculate the speed restriction for 2-degree curve on a broad gauge section with a maximum permitted speed of 100 kmph per hour. So section speed is 100 kmph, curve is 2 degree. But here, due to space restriction, the length of the tension is limited to 50 mm. And superelevation provided 60 mm. They are given everything. So actual superelevation provided, they are given actual superelevation 60 mm, and curvature, degree curvature, we got to convert into radius. Okay, then sectional speed 100 kmph. But whereas here the length of transition restricted to 50 meters. Okay. Yes, right away we can work it out our maximum permissible speed using the relation. So Vm equal to 0.27 root of Ca plus CD R. Since CD is not given, and we are assuming a CD of 75 mm. Okay, 75 mm. And since the degree of the curvature is 2, and converting to radius 70 divided by 2 degree 8 centimeter radius. Okay. Then use the relation 0.27 into root of CA. CA is given, this is 60 mm, and CD we are permitting up to 75 mm, and R is 875 meter, and substituting here we get the maximum permissible speed on the curve is coming around 92.79, say 90 kmph. Okay, since the sectional speed is 100 kmph, then we cannot permit this much, and we are restricted to 90 kmph on the curve. But however, this length of transition is restricted to 50 meter here. That is why we have to do a check now. So in this, when we are providing cant actual of the 60 mm and for the speed of 90 kmph, whether the length of transition is sufficient. Okay, when 50 meter is provided, whether it's sufficient. So the perimeter range of rate of change of cant actual cant efficiency for the restricted phase normally 60 mm per second. So already we have discussed the rate of change of cant actual cant efficiency for the restricted phase is 65 mm. Desirable is 50 mm, but here since it's restricted, we are availing 60 mm per second. Once we have 60 mm per second, this is a length of transition formula. 5 by 6 of 0.0056 into Ca into Bm is the rate of change of cant actual consideration, and rate of change of cant efficiency consideration. This is your equation. And also one more equation we gave, cant gradient. Okay, For the restricted speed, we can have a can gradient of 1 in 360, and accordingly we have the equation of 0.36 into CA. Okay, so we are substituting, the in this equation whatever CA, the given problem equation CA, and VM, 90 kmph. Substituting here in the first equation, we got 20.2 meter, and the second can deficiency, let us can consideration. Okay, 75 we are permitting here now. With this, for the speed we are working out, it's coming around 31.5 meter, and based on the can gradient 0.36 into CA, we calculate it's coming around 21.6 meters. So out of the greater one you have to choose. So if that is the case, then we have to provide how much? 31.5 mm, 31.5 meter. But whereas the transition, it's limited to 50 meters, so we can go up to 50 meter. So actually the requirement is less than the permissible limit of length of transition, and it's okay, no problem. So we can provide 50 meter transition, you can provide. At the same time, for the superlight 60 mm, and we can run the train at a speed of 90 kmph. Okay, on curve. Okay, this is something about it. Okay, let's see another problem that is also from UPSC Engineering Service, year 2022. Here, a 400 meter radius curve is introduced between straight portions of a broad gauge railway line intersecting to form a deflection angle of 50 degrees. The speed for determining the equilibrium current is fixed at 100 kmph, and the maximum sectional speed is 120 kmph. So determine the equilibrium current and MPS, maximum permissible speed, and desirable length of transition curve. And they are given limiting values of cant, that is 165 mm, and cant deviation 100 mm, and cant is restricted to 75 mm. The lowest speed of any train has to be taken as 50 kmph. So these are data given. The data, then we have to go ahead to find out the equilibrium cant. Then what is the actual cant to be provided? Then we have to find out the permissible speed on curve. Okay. The radius is 400 meter, deflection angle 50 degree, but we'll see where I can use this one. I don't think we need this deflection angle anyway. The sectional speed is 120 kmph and lowest speed is 50 kmph. The equilibrium speed 100 kmph. So for this speed you have to find out the equilibrium current. The limiting values of cant actual, cant deficiency, cant X also, they can 165, 100 and 75 respectively. So first we have to find out the equilibrium cant. So we can use the relation GB squared by 127 or 13.76 for BG, 13.76 into V squared by R. Here we have to use the speed equilibrium, that is 100 km they are given. So substituting here, and we can calculate our equilibrium current. That's coming around 344.49 mm. So this is equilibrium current. But we cannot provide this much because already the maximum current has been restricted to 165 mm. Okay. So first let us try to fix cant actual based on the cant deficiency consideration. That means cant equilibrium equal to cant actual plus cant deficiency. This much cant we can, deficiency we can permit. So cant actual plus the permissible cant deficiency equal to the total requirement of superelevation, that is equilibrium cant 344. Then and that you can find out the cant actual. In this case, 344 minus 100 you will get 244. Even 244 also we can't provide, because maximum superelevation has been restricted to 165 on. Okay, so cant deficiency consideration, cant actual we can fix up to 165 mm. Okay, now we'll go for cant X consideration. In cant X consideration, this is a equilibrium cant required for the lowest train, because normally cant X consideration, we have to calculate super is required for the lowest strain. Here the data they given, the problem they given 50 kmph. So for 50 kmph we find out the current required. Then total current required. But you can go up to excess we can permit. That means we can add some more this one, can't access. The limiting value is not way. Okay. So in this case, the can't actually equal to the requirement for the lower speed plus the permissible can't access scientific, then comes to 161 mm. But normally, should be in a multiple of 5. Lower side we are fixing, rounding up to 160 mm. So out of the current efficiency and current access constraints, lowest we have to consider. Hence, we are providing current actual of 160 mm, so that it will satisfy both the conditions. Current access consideration as well as current efficiency constraint will satisfy when we are fixing 160 mm. So once we know the current actual, already in the permissible limit of current deficiency also is given, it is 100 mm. So we can use this relation Vm equal to 0.27 root of Ca plus Cd into R. Already with Ca already we have decided, so 160 mm. Current efficiency it is given the problem, then 400 meter radius of the curve, it's also in the problem. So substituting here, now we are getting the Vm, that's coming around 87.07 kmph, say 85 kmph. So lower side, multiple of 5 we are fixing, so say 85 kmph. Since our sectional speed is how much? I think it is 120 kmph. So 120 we cannot permit, no. So that is why we need to impose speed reduction of 80 kmph on the curve. Okay. This is up to the Vm. Then they asked desirable length of transition also in the problem. So desirable length of transition, and we know pretty well that we have 3 equations. Out of 3 equations, 3 formula now, the greater value we have to choose. The first one is based on the rate of change of current actual, that is 0.0056 into C into Vm. Second one 0.0056 into CD into Vm, that is rate of change of current efficiency consideration. So 0.0056 into CD into Vm. The third one is based on your current gradient, that is 1 in 720 current gradient. Okay, 3 equations. The first formula we are substituting here, current actual 160. We are providing, we have calculated as Ca, and 85 is the permissible speed on the curve. So substituting here we get the L1, that is for the first condition we have the length of transition equal to 76.16 meter, and second conditions we got 47.6 meter. For third conditions here 0.7 to 160, that is 115.2. Okay, here current efficiency and mm we have considered here. Okay, so out of 3 the greatest one is this one, the last one, based on the current gradient. So 115.2 meter it's coming. So again, normally our station units are in 10 meter, no, that is why the multiple of 10 only we must have. Higher side fixing 150, no, let's say 120 will be our length of transition. Okay, this is something about this problem. Okay, so once again just you can slowly study and understand. Okay, now let's go to the next problem. This UP Civil Service Examination 2016 they asked. Here, what would be the equilibrium current on the curved BG track with 2 degree curve on average speed of 70 kmph? Calculate the minimum permissible speed after allowing a maximum current deviation of this much. 2 centimeter means 20 mm. Okay. But here you see it's direct questions. There is no, complicated. They given degree, we can convert to the radius, that is R. The R is given. The average speed, they are given 70 kmph. So for this, you have to find out the current equilibrium. Okay. So the equilibrium current, we can use this relation of 13.76 V squared by R, it's being BG. Okay, BG track. So we can take the average speed they given 70 kmph. Substituting here and R also 875, then our equilibrium current will be 77.06 mm, say 80 mm. Okay, this will be our equilibrium current. Then let's you can provide 80 mm current and maximum permissible speed. So the equilibrium current is this much, and that we are providing this much superelevation, and current deficiency as problem, they are given 2 cm, that's 20 mm. So considering the current deficiency of 20 mm, we can find out the maximum permissible speed, which is the relation 0.27 root of Ca plus Ed into R. R is 870 meter. So 79.89 km is say 70 km. Okay, rounding up to lowest 5 multiple, that is 75 km. So we have calculated but we have calculated maximum permissible speed. I think not minimum. That's the maximum permissible speed on the curve is 75 km. Okay. This is something with this problem. Let's go to the other problem. This is a IFS 2018. They asked this question. This is also a direct question. Simply calculate the maximum permitted speed on the curve MPS on curve high speed broad gauge track group A using the following data. They given degree of the curve, we can get radius and superelevation 85 mm. They given current also, the length of transition also they given, the maximum suction speed also they given, the suction speed and current deficiency this thing. Okay. So here 2 degree we are converted into radius 870 meter. Okay. And superelevation they given is actual superelevation provided is 85 mm. And length of transition curve is 120 meter. And maximum suction speed is 160. Suction speed is 160 kmph. Current deficiency is mm. So from there, using our relation Vm equal to 0.27 and root of Ca plus Cd into R, we can find out the maximum permissible speed on curve. So here the problem they given Ca and Cd also they given 100 mm. So R is there. So straight away we can get the maximum permissible speed on curve, that is 105. But our sectional speed is 160 kmph section, but we cannot permit 160 kmph here. So necessarily we have to impose speed restriction of 105 kmph, okay, on the curve. And also since they are given length of transition, but nowhere we are used. But you have to use this transition curve, length of transition for check. Because sometimes what will happen when they give transition, length of transition, sometime it may be results to some restriction. Okay. So, but here I think it is 120 mm is very longer length. If it is very short, so when you are working out for this condition, our length of transition will be sometime more than the provided one. In that case, necessarily we have to restrict our current efficiency, everything. Okay. So that is we have to do some check also here. Okay, since they are given length of transition, we can cross check. So check for transition length. So length of transition 120 meter. So perimeter rate of let's change calculation. Restricted space is normally 60 mm per second we are using, and for this condition, this is the relation we got. 5 by 6 of 0.0056 C into Vm and 5 by 6 into 0.056 CD into Vm, and since restricted space, we normally we are going for the minimum length, that is why. So 1 in 360 gradient, that is L is equal to 0.36 CA. So this using these three relations, we are substituting the value, we are getting the length of transition. The greatest one we are considering, that will be our required length of transition. Here CA already given the problem, and VM also we have calculated, it's 105, and CD also it's given in the problem. VM we have already calculated, and CA it is also given. So substituting everything, first condition 41.65, second condition 49 meter, and third condition is 30.6. But almost whatever we got now, there is greatest one is here 49. But the 49 is actually it's less than the provided. So the requirement is only 49, But whereas the example, problem, the length of transition is 120 meters, it is very much, more actually than the required. That's why it's okay. Okay. So whatever CD consideration, CA calculated and the VM calculator and all, stands good. Okay. Hence, so whatever already calculated the max permissible speed, only we can permit. Since it is 160 kmph section speed, so we have to impose speed restriction of 105 kmph. Okay. This is something about it. Next, this is from UPSC Civil Service Examination 2018. Here it is, this is a problem. A branch line takes off from a main line. Okay. Here they have not told anything about the turnout. They are given straight away a 6-degree curve branches off from the 3-degree main line in an opposite direction. That's contraflexor in the layout of VG yard. If the speed of train on the branch line is restricted to 35 kmph, determine the speed restriction on the main line. Assume permissible candidate efficiency as 75 mm. Okay, this is the problem they are given. So degree of branch line how much? 60 degree they are given, and degree of main line 3 degree, and branch line speed 35 kmph. CD parameter 75 mm. So it is a contraflexor problem. So here the RM means how much? Radius of main line. So we are converting to from degree to radius. So 1750 divided by 583.33 is a main line curve radius, and branch line curve radius 1750 divided by 6, that is equal to 291.66 meter. Okay, the radius of branch line. Okay, this is our main line. This is your branch line takes off, contrary flexor. This is your curve degree. Radius is degree is 3 and radius is 583.33. This degree of curve is 6 and radius is 291.6 meter. Okay. So can to be provided how much? Since it is a contraflexor, so you have to you are in the compulsion to compromise situation. So whatever supply you are providing should satisfy the both the trains which are negotiating, the turnout as well as the main line. Okay. Here first we are finding out the can't record the branch line. So using the relation G square under is or 13.76 and B squared by R we are using it. And we are substituting the turnout speed, how much permitted, that is 35 kmph. Substituting here and substituting the radius of the branch line. So we are calculating the cant required for the branch line, that is 57.88 mm. So here what we are doing, as I already told when we are providing a superelevation to the turnout, that will become negative superelevation for the main line. But when you are providing superelevation for the main line, that will become negative superelevation for the branch line. But normally, we are running train at higher speed and the main line normally. So main line we should try to give superelevation and compromising the provision of superelevation in the turnout side, duly availing the cant efficiency. So instead of providing 57.88 mm cant, we are permitting the cant efficiency of maximum in the turnout, and so that instead of providing positive cant, we are providing negative cant in the branch line. So how much we are providing? 57.88 required, but cant efficiency when we are permitting, we can still instead of rising the outer rail, we can lower in the outer rail by providing negative cant of 17.12 mm. Okay, so that the trains running in a turnout 30 kmph, the requirement is 57.88, but whereas 17.12 only we are negative cant will be there, and thereby there will be cant deviation 70 mm, that is permissible limit. Okay, so whatever negative cant we are providing in the turnout side, that will become positive cant to the main line. Okay, this has been already discussed in the previous problem, the time of covering this area, this topic. And here, hence, the 17.12 will be your cant positive cant provided in the main line. Say 15 mm, you can provide 15 mm. So I think in this area you should understand properly. Okay. So negative cant, we are providing negative cant to the this one branch line, availing the cant efficiency. That means the 15 mm. That 15 mm will become positive cant to the main line that we are providing. So once this is your cant actual, so we can permit a cant efficiency of 70 mm, and further we can find out the speed permitted. So cant efficiency, the permitted is 75 mm using the relation 0.27 root of CA plus CD into R. So actual is 15 cant actual and plus 75 cant efficiency. And radius of the main line curve, you take here main line radius of the curve, because we are finding out the speed required for the main line 583.33, and it comes to 61.86 kmph. So say 60 kmph. This is the speed parameter on the main line because of the contraflexion. Okay. And the other one is, this is UPSC Engineering Service 2017. Here this also like contraflexion, contraflexion problem. Here they are given only 12 turnout they given. Okay. Previous question they are given directly some branch line radius, but here they are not given the radius of the branch line. Okay. They are given the on the points on crossing which falls on the curve is 1 in 12, but it takes off as a contraflexor. Okay. For a 2 degree main line curve, and the branch line speed restricted to 45 kmph. Okay, and main line how much speed permissible they asked. The permissible cant efficiency we can take as 75 mm. Okay, so here degree of the main line 2 degree. Okay, we can convert into radius, that is 8 centimeter. This is speed permitted in a branch line. CD 75. Already given, it is a contraflexor. Okay. So and also radius of 1 in 12 they are not given here. They 1 in 12, but we should already we have discussed. They are given on slide also. There were various turnout. What is the late curve radius? Here the radius of 1 in 12 turnout is 441.36 meter. Okay, that we have to take it. Okay, the problem not given, we have to approximate, we have to assume, and we have to proceed. Okay. Then resultant radius equal to, because the turnout only they are given. The turnout means this radius of straight turnout. This whatever radius, this is for the straight turnout. But if when we are fixing in a 2 degree main curve, automatically this radius will become, what will happen? It will become flatter, because the entire, because the straight main line, the turnout main line is also has to follow the curvature of the main line curve. Once it is following, automatically entire set will be shifted, deflected towards the main line curve. Automatically the resultant radius will become flatter. Okay, it is 441 means it will be flatter. Okay, when it is contraflexor normally. So this has been already also discussed. Using the relation RR, RM into RS, RM minus RS, we can find out the resultant radius. So substituting here, 890.57 will be resultant radius of the turnout here. So 875 is a degree of the main line, and 441 the radius of the straight turnout. And because of the flexing, this also the curvature, turnout side curvature also it just shifted towards the main line curve, and because it becomes flatter, and thereby the resultant is becomes 890.57 meter. Okay. Okay, this is your main line. When straight turnout is there, the radius will be 441. So once the main line that of turnout, just it is also bending this way, automatically this line also will be pulled this way, thereby this curvature will become flatter. Okay, so finally the resultant radius we got 890.57 meter. But now we have to find out the cant required for the turnouts. So what is the speed permitted on the turnout? 42 kmph. So substituting here, we can find out the cant required for the turnout. usually GV square 121 you know R is our resultant turnout radius, 42 kmph speed on the turns given the problem. So substituting here we are getting the cant required for turnout, it's coming around 27.2 mm. Okay. Again contraflex, I already told you know we can permit a negative cant in the turnout, so that to ensure positive cant to the main line. So availing the full cant division of 75 mm, we are permitting negative cant of 47.1 mm, 7 mm for the turnout side. Okay, and ultimately this will become positive cant for the main line. So instead of 47.71, we are actually providing 45 mm to the main line. Okay, this is whatever now, this is positive cant we are providing in the main line. Of course, it is the negative cant of the turnout side. Okay, though we are negative cant of this much, 27 mm required, but thereby there will be a cant x, I mean, what do you call, cant divisions. Cant divisions are only 75 and less only, which is permissible. So this cant provided in the main line is now 45 mm. And once we know the cant actual for the main line and availing the cant divisions of 75 mm, substituting the formula 0.27 into root of CA plus 80 into R. R is this is the radius of the main line. Radius of the main line. So substituting everything, we got the maximum permissible speed on the curve, say 85 kmph. Okay. This is about the problem. I think let us conclude this video. I hope I think whatever explanation I given would have satisfied you. Thanks a lot. Let's see in the next video. I will the further some left out topic of curve I will discuss. Okay. Thanks a lot. Thank you.